I've got one there.
I could try to find you a more comfy one if you want.
It's all right. Be good. Thanks. All right, ready to get started? So welcome. This is STAT636, Applied Multivariate Statistics. I'm Dr. Dabney, Alan Dabney. I have been here at the Statistics Department since 2006. I'm from Texas. I got an undergraduate math degree at University of Texas at Arlington, and then my PhD in biostatistics from the University of Washington. I've taught this class now 4 or 5 times. I teach it in the fall for the past 3 years, and it's an audience like this one, which is a mixture of local students and also following along online is about as many of you as are here in the class who are getting their master's in statistics at a distance. So we have a little over 100 students this semester. Most of the folks who are in the classroom are from other departments, is what typically happens. Graduate students from non-statistics departments. I am happy to see that we do have some statistics graduate students in here this semester, and I know we have a handful of statistics undergraduate students as well. Let's see. So I thought what I would do today is go through the syllabus a little bit and give an overview of the course, and we'll get started in our first set of notes. So let me get the syllabus. Under course content is syllabus. Pretty much everything we need is going to be under course content. Notice that there's a folder for data, there's a folder for notes, that's lecture notes, and a folder for scripts. We're going to use the statistical software package called R in this class. I'll say a little bit about it when we're in the syllabus. But R is open source, which means it's free to you to download. And it's an interpreted language, kind of similar to MATLAB. So if you have experience with MATLAB or Python, it should come fairly easily to you. I do have some tutorial references that I'll point you to. There are a couple of online tutorials that are free to you that would be good if you're brand new to R, to get your feet wet with it. All right, so our syllabus. Hi. My office and email are listed here. My office is just around the corner. And regarding office hours, I haven't put any specific times down. I can if you really want me to. But what I typically do is just say, if you have questions, send me an email and let's set a time for you to come see me. I'm very flexible about when we meet. I'm happy to meet whenever. Just let me know. This class is all about multivariate statistics. So what is multivariate statistics? I'll say something about that when we get into our notes. But basically, multivariate means you have more than one variable that you want to characterize simultaneously. So we might, for example, be interested in modeling the price of Apple's stock. So we could draw pictures, histograms, and time course pictures of the stock price of Apple. We could do t-tests and stuff. What is the average stock price of Apple in the summer versus not in the summer? We could do linear regression. Let's try to model the stock price of Apple in terms of certain market events, like Was there high volatility, or was there a major disaster across the globe or something? All of that stuff is univariate statistics in the sense that we're talking about one response variable, which is the stock price of Apple. And I want to characterize that one variable. Multivariate is when there's more than one. For example, suppose we wanted to characterize the stock price of Apple and the stock price of Microsoft and the stock price of Netflix. All of them together. Let's draw pictures that show their joint relationship over time. Let's do t-tests to compare the triplet of averages in this condition versus that condition. Or let's do linear regression where the response variable is a vector. Those are all multivariate problems. Why should you care about multivariate problems? Most data sets nowadays are multivariate. If you download a data set, you have an Excel spreadsheet with individuals in the rows, and then you have variables in the columns. Most any data set nowadays is going to have lots of columns, lots of variables. So viewed that way, your data set is almost certainly multivariate already. Suppose we had a spreadsheet with rows representing weeks and columns representing 5 different companies whose stock prices we're monitoring. I want to talk about Apple, I want to talk about Microsoft, and these others. One possibility, one strategy, would be to do one at a time. Let's look at Microsoft. Here's what I found. Let's look at Apple. Here's what I found. And then in kind of a post hoc manner, tie the results together. I saw a seasonal component to Apple. I also saw a seasonal component to Microsoft. So I kind of make a multivariate inference just by comparing those two univariate inferences. The reason you care about multivariate statistical techniques is that generally speaking, you can extract more information, get a richer picture of relationships and interrelationships by considering your variables together simultaneously. If I looked at Microsoft on its own, and then I looked at Apple on its own, I could say individually, here's what Microsoft is doing, here's what Apple is doing, but I can't talk about how they are interacting with each other, and I may not be able to pick up on more subtle patterns and relationships that only are revealed when you look at them simultaneously. So general principle is if you are able, a multivariate analysis is probably going to give you more information than a set of individual univariate analyses. Multivariate statistics will the toolbox for this is composed of many different types of techniques, ranging from exploratory techniques, like if you just want to make pictures of a data set, how do you visualize a data set, to inferential techniques like t-tests and ANOVA. How can you do t-tests and ANOVA when your response is multivariate, a vector instead of a scalar? To predictive modeling, like discriminant analysis. Let's try to predict whether you have cancer or not based on a vector of observations that are gene expression numbers. Quantify your 30,000 genes, multivariate, and try to predict, based on your profile, whether you have cancer or not. That's called discriminant analysis. Or we might want to predict a numeric variable or a vector of numeric variables. Here's my vector of stock prices for 5 different companies, and I want to, as a function of a collection of input variables, what was the market volatility this week? Were there any major catastrophes around the world last weekend? Those types of inputs. I want to spit out a predicted vector of stock prices for all 5 simultaneously. That prediction stuff, whether we're predicting a categorical variable like cancer or not, or a numeric variable like a vector of stock prices, that has different names, and it's very hot as a topic right now. So you will hear that described as machine learning, statistical learning, supervised learning, classification, predictive modeling. All of those things, to some extent, fall under the umbrella of multivariate statistics. So we will be covering those to some extent in this class. But that's not what the whole class is about. So I suspect, based on previous semesters' experience, that some of you are keen to learn advanced machine learning techniques like support vector machines and neural networks and such. We won't have time to get into those advanced topics in much detail at all. Multivariate is a much bigger discipline and set of tools. What we will see are classical exploratory techniques like principal component analysis and cluster analysis and factor analysis and methods of ordination or dimension reduction. Those are extremely useful, bread and butter kind of techniques that I think you should plan to apply to any data set. Step one when you have a data set, by the way, is not to go compute p-values or build predictive models. Step one should always be to explore and visualize the data, investigate it. There was a famous statistician named John Tukey who kind of pioneered the idea of exploratory data analysis, or EDA. And it is just the idea of kind of being a detective, looking at the data from different angles, trying to find unusual patterns or individual observations. Are there outliers? Are there missing data? Do the relationships go in the direction that I expect, or is there something counterintuitive? If there's a major problem with how the data were collected, you may not discover it if you don't look at the data in an exploratory way. So one of the most valuable components of this class, I think, is the collection of exploratory techniques. Principal components and cluster analysis in particular. I apply those to any data set I get nowadays. They're just a great way of taking a big multidimensional data set and turning it into an interpretable picture that conveys a lot of information. So, all right. Prerequisites, I expect everybody in here to know what regression is, to know what t-tests, p-values, confidence intervals are, and you need to have some familiarity with linear algebra. Not on the level of abstract vector spaces or anything like that, but basic vector and matrix operations. How do you multiply matrices? How do you invert a matrix? What's a determinant? What's an eigenvalue? What's an eigenvector? That will take you a long way in the class. If you're not familiar with those concepts, we will have a little bit of review in class. The textbook has a primer also that you should review. Okay. I mentioned that half of the class is online, and particularly relevant to them is that on Monday nights, 6 o'clock to 7 o'clock, down at the other end of the hallway of this building in Blocker 411, I will hold like an online office hour. So the idea there is that it's an opportunity for distance students to log in and communicate with me in real time. So it's they have the ability to either talk over the microphone or chat with text, but basically ask questions as you would do if you were sitting across from me in my office hours. While this is primarily intended for the online students, everybody's welcome to come. Last year I had at each Q&A 3, 4, or 5 local students who came, because it is a good opportunity to get tips on homework and get some general questions answered. We do have a TA I'll post it on eCampus. His name is Riddy. And instead of office hours, he's been assigned to man what we call the help desk, which I forgot what room it's in, but I'll post it on eCampus. But there's a specific time period each week that you can go to an office in Blocker, and there are graduate students from the statistics department who can help with whatever class. And Riddy is going to be your go-to person for this class. Okay. So I do want you to get a copy of this book, Methods of Multivariate Analysis by Renscher and Christensen. It does not matter to me whether it's the latest edition, so feel free to get an old edition. We are going to use R. I have a link there in the middle of the page to where you can start with R. Go to that page, there's a big button that says download, and you just pick the right release for your operating system, for your type of computer. It's like 30 megabytes, not very big. Download it, install it. When you install it, it looks like this. So it's an interpreted kind of console-driven software. So if I type 1 + 1, it does the arithmetic. If I want to create a variable, like a vector that is the numbers 1, 2, 3, I can create a variable called x, and now every time I say x, it knows that it's a variable. There's two main flavors of R. This is the basic R console version, which is what you'll find at the URL from the syllabus. This is what I use. There is an alternative called RStudio, and what it does is basically put a few bells and whistles on top of this. So RStudio, it's also free. When you open it, though, you'll have 4 panels. Instead of just the console, you'll have a panel that has the console in it. You'll have a panel for any graphics that you want to launch, a panel for help files, and a panel of like a directory view showing you the objects that are there. Some people find RStudio more intuitive or easier to use. I don't. I like just the base R. It's up to you. Either one will get the job done for our class. While I'm on the topic of R, there are a couple of resources that I want you to know about. There is a website called Code School, codeschool.com. And there is a free course called Try R. I think you have to create an account, but it's free. You can just create a free account, and then this course does not require a premium account. The course is composed of lecture videos, and you'll get lectured at a little bit, and then it will change change gears, and it will open up a console through the web browser and ask you write some code to make a histogram or something. And you have to be able to write the code before you can move on. So I think it's a great way to just get your hands in to R and you get a real basic feel for it. It's about 3 hours total to complete this thing. Another resource is through Lynda, Lynda. Lynda is an online repository of training videos and courses. You have access to this already. It does not require that you buy anything if you go through A&M. So A&M has a site license. So if you go to lynda.tamu.edu and sign in, there are at least 2 R-related tutorials in Lynda. If I remember, I'll post the specific title of the 1 or 2 that I think are best. But there is one tutorial in Lynda for R that I think is pretty good. There is also a book called the R Cookbook that I like. This book, I'm pretty sure you can get the PDF, the ebook for free through the TAMU library system. So if you go to library.tamu.edu and search for R Cookbook, you should be able to get the ebook. It's not like an expository textbook, it's a cookbook. So if I want to make a histogram, I go to the section how to make a histogram, and it shows examples. So it's very kind of practical. All right. We will have homeworks and we will have exams. Homework's going to count 30% of your grade. You are going to submit your homework through eCampus. So in eCampus, you'll see homework assignment 1, and there will be a link for upload your submission. So everybody should submit a PDF through eCampus for every assignment. I'll mention this a couple of times throughout the semester, but it'll help me and the TA save us some time if you save your file in the format last name _ first name.pdf. Just makes it save several minutes every time we have to grade, so please make a note and try to remember to do that. There will be 2 exams, each worth 35%. First exam is on Wednesday, October 11th, and the second is on Monday, December 4th. So the second exam will kind of take the place of a final exam. I'm not going to have a comprehensive final exam, just 2 exams. For the exams, you will come to class and you will download a data set from eCampus. So for each exam, I'll have a data set ready for you. You'll get a PDF from me that you'll open up on your laptop, download such and such data set, and 1, 2, 3, 4, 5, do these 5 things. Make a picture of this versus that. Compute or tabulate such and such. Do principal component analysis and interpret the results. Make a dendrogram and interpret the results. And what I want from you is to use your computer or one of the computers in here to use R to do what I ask of you in the exam document. The exams will be open everything. That means you can look at the notes, you can look at my R code, you can use the internet, anything you want, except that you can't communicate with each other or anyone else. So no phone calls to your uncle with a PhD in statistics, no talking to the people next to you. And what I recommend is that you create a Word document and copy and paste any R output that you need, any R graphs that you need, build up an R or a Word document, save that as a PDF, and upload that to eCampus. All right. Here's our schedule. This week we're going to give a real brief introduction to multivariate stuff. I'll do a quick review of the important linear algebra, vectors and matrices, and basic operations. I'll introduce the idea of a random vector. So if you've had an introductory statistics class, you know what a random variable is. Stock price of Apple, for example, if you view it as an unknown quantity, I'm going to measure it once a week, say, then you could say that the stock price of Apple is a variable because it's going to take different values, and it's a random variable because we believe that its price is subject to random variation. We could put a probability distribution on it then. The probability the stock prices between this and that is estimated to be such and such. It's a variable whose outcome is subject to randomness and uncertainty. That's a random variable. The natural extension for multivariate statistics, when it's a vector instead of a scalar, is a random vector. The stock price of Apple and Microsoft and Netflix and these 5 stocks, viewed as a random collection, is essentially a vector of variables, all of whose values are subject to randomness. So we're going to talk about random vectors. That's the basis of doing multivariate t-tests, multivariate regression, multivariate ANOVA. Whereas I could put a probability distribution on a univariate variable, like stock price of Apple, when I go to a random vector, I can still put a probability distribution, but it's more complicated now. It's a multivariate distribution, because I'm not just talking about the stock price of one stock. I'm talking about the prices of a vector of 5 stocks. So imagine putting probability on a 5-dimensional space of possibilities. If you understand the basics of probability, the basics of random variables, and the basics of probability distributions, for our purposes, you should be able to at least mentally extend things to the multivariate case. I'm not going to go heavy into the mathematical theory behind much of anything in this class. The emphasis is on application. But to the extent you can understand what's going on behind the scenes, it'll help you. The better you understand the tools, the better able you'll be able to use them intelligently. So this week is an intro to multivariate stuff, a review of linear algebra, random vectors, and I'll also spend a little time kind of holding our hands as we get used to R. Next week will be a fair amount of R. And what I plan to do is show you some basic computational techniques that have a lot of utility in statistical analysis and data analysis, namely simulations and resampling techniques. So a simulation is like, let's generate, suppose you have stock prices of Apple over the past 5 years weekly, and you want to know what's an appropriate statistical method for estimating the average yearly time course. Suppose you have some ideas for possible ways to go, but you're not sure of the theory, or you're not sure whether that's a rigorous approach. One thing you can do in any case is simulate data that are like your real data. If you simulate 5 years of weekly stock prices, then you could just apply any technique you want to try and see what happens. The idea of simulation is that you would simulate the 5 years of stock prices once, apply your technique you're considering, and record the output. Then repeat. Here's another simulated set of 5 years, and another, and another, and another. If you do that many times, thousands of times, say, then you get to say things like, the average performance of the method I'm interested in is to do such and such. Simulations are a really valuable way to investigate many things in data analysis and statistics, and R is great for doing it. Resampling techniques, what I have in mind is a couple of things, one called the bootstrap and one called cross-validation. The bootstrap is a general technique, computationally intensive, for getting standard deviations and what we call sampling distributions of an arbitrary statistic. When you learned statistics in Stat 101, you were taught about the standard normal distribution and the t-distribution, and they were relevant because they were the sampling distributions of a very common statistic. either the sample mean or the standardized version of the sample mean. What computers make easier for us is they free us from having to make some restrictive assumptions. That t-distribution, standard normal distribution, those are great and they work well and they are sampling distributions under certain assumptions. So wouldn't it be nice if there was ways to do the same basic thing, get confidence intervals and p-values without having to make assumptions, or at least such strong assumptions? The bootstrap is a resampling technique that is all about that. So I want you to know about it. It's applicable to virtually every kind of statistical analysis, whether it's univariate or multivariate. All right, then we'll spend a couple of weeks on multivariate inference. By inference, statistical inference, that's jargon. By that we mean p-values and confidence intervals. I take sample data that were obtained from some population of interest, and I use the sample data, which is incomplete, it's not the whole population, it's a randomly obtained representative sample, but I use it to make confident statements about the population. That's statistical inference, a really core set of tools for doing statistical analysis. T-tests, linear regression, ANOVA, those are all inferential techniques. So we'll learn a little bit about how to extend those to multivariate settings. Then we'll get into exploratory stuff. So principal component analysis and factor analysis. They're related to each other. Principal component analysis in particular is a technique for taking a vector of numeric variables and visualizing it. So suppose we have the 5 stock prices. I have a data set full of 5,000 weeks, and each week I have these 5 stock prices. Multivariate data set. Let me draw something real quick on the board while I'm thinking about it. Okay. So we're going to talk in this kind of language throughout the class. We're going to say, I have a data set and I'm going to use the symbol X to represent the whole data set. So this is a matrix, or in R we're going to call it more generally a data frame. Basically, it's an Excel spreadsheet represented by the letter X. And we're going to use the notation that X has n rows and p columns. In the rows are the individuals from our sample. If I want to study female CEOs in the US, the population I'm thinking about is the collection of all female CEOs in the US. And if I wanted to really definitively answer what's the average salary of those people, for example, I would need to go talk to every single one of them, the entire population. Alternatively, I might take a random sample. Here's the yellow pages of female CEOs. I'm going to randomly pick 250 of them. My sample size, N, is 250. So in the rows are the individuals that constitute our sample. P, the number of columns, corresponds to variables. For each female CEO, we have their age, we have their years of education, we have their annual salary, a bunch of different variables. So get used to the notation of X being an n by p matrix. Generally speaking, the p columns could be a mixture, and often will be a mixture, of both numeric and categorical variables. It makes a difference in terms of what we can do statistically. Remember that a numeric variable is just a variable you can do arithmetic with, whereas a categorical variable, arithmetic doesn't make sense. There's no such thing as average gender, average hair color. Zip code is a number, 77845, but it doesn't make sense to do arithmetic with zip codes. So categorical, it's just arbitrary labels for different categories. Numerical, you can do arithmetic. Okay. So suppose we had in the columns all p of the variables are numeric. We're going to see a set of tools that apply to numeric variables and a separate set of tools that apply to categorical variables. There are some statistical tools that apply to both simultaneously, but there are some that only apply to one or the other, but not both. Where I was going here was to introduce the idea of principal component analysis. Suppose we have that data set, X, n by p matrix of numeric variables. It might be 50,000 rows by 20 columns. Big data set, that's not even that big nowadays. But certainly with 50,000 rows and 20 or 200 columns, there's no way in the world you're going to use your eyeballs to learn anything about it. You can scroll through the spreadsheet all day. You won't, your brain's not wired to extract any kind of systematic patterns or information from such a large data set. So the idea of exploratory data analysis with multivariate data often turns into kind of a dimension reduction task. Let's take this big Excel spreadsheet and let's somehow cram it down into a two-dimensional scatter plot or some other two-dimensional representation, or maybe 3 dimensions. Principal component analysis is all about that. Given a set of p numeric variables, which I can't visualize because it's too high dimension, can I turn those p variables into 1 or maybe 2 or maybe 3 new variables that are carefully constructed such that those handful of variables, much smaller dimensional footprint, give me essentially the same information as the whole data set. In terms of joint relationships, major patterns, trends, is it possible to take p numeric variables and cram them down to 1, 2, or 3 that essentially get across the same information? If so, then you could take your 50,000 by 200 matrix of numeric variables and do the principal component magic to it and get, say, a two-dimensional scatter plot. And the scatter plot is informative. It tells you this axis is the most informative. This one's not quite as informative, but it's still informative. And every individual, all 50,000, have a point on the scatter plot. So you can visually see how the data set spreads out, which individuals tend to group together, which individuals are different from each other. You can learn a lot. Factor analysis is similar to principal component analysis. I'll wait until we get there to highlight the distinctions, but both of them are kind of similar idea. Let's start with a collection of numeric variables and let's discover new numeric variables that I can use to represent the whole data set, at least with high fidelity, without losing too much information, but using just a handful of variables instead of the whole collection. Dimension reduction. Cluster analysis is all about discovering how items group together. For example, suppose the stock price setting. Can we take 50,000 rows by 5 columns, numeric stock prices for the past 50,000 time periods, and discover here's a set of time periods, maybe they're days of the month, that group together. On this collection of days, what you see is Microsoft and Google are above average, and Apple and Netflix and such are below average. And then maybe there's another clustering or grouping of days on which that relationship is switched. And maybe there's yet another grouping where everybody's the same except Netflix, which stands out for some reason. The idea of cluster analysis is to discover groupings. Okay. Canonical correlation, multidimensional scaling, and correspondence analysis. These are more exploratory techniques. I'll talk more about them as we go. Then we'll spend 4 weeks, 4.5, on predictive modeling. Because based on my past experience with this audience, I know a lot of you are interested in predictive modeling. Data mining, supervised learning, that type of stuff. So we'll spend a good amount of time on that. When we get to that material, I'm going to be referring to a book that I recommend you get a copy of, Introduction to Statistical Learning. It's available for free online. I just Googled the title, and the first hit was Gareth James' homepage at Berkeley. He's one of the authors, and they have kindly made the book available for free by PDF. It's all about predictive modeling. Let's predict a numeric variable. Let's predict a categorical variable. And ranging from very simple, like linear discriminant analysis, up to fairly sophisticated, like random forests and support vector machines. The book is all about, or it uses R exclusively, and they have a lot of code. So we'll definitely make use of that when we start talking about predictive modeling later in the semester. I'll organize our predictive modeling stuff into, let's talk about the big picture. If the goal is predictive modeling, there's a set of common issues that we need to be familiar with. You don't want to overfit your training data, for example. How do you measure accuracy of a predictive model? Should you use classification accuracy? Should you use the false positive rate, the false negative rate, ROC curves? There's all kinds of things that we want to be kind of familiar with. And then we'll talk first about the context of predicting a numeric response, like a stock price or BMI or annual earnings. And then we'll split to the categorical case, which I think these days is more common. You're a credit card company, and based on a vector of input variables like what's the client's age, gender, credit score, average monthly balance, those types of things, let's predict whether this new transaction that just came across the wire was a fraudulent one. Predict, yes or no, categorical, was this a fraudulent credit card transaction based on input variables? That's classification, or predictive modeling with a categorical variable. Let's predict based on your genetic profile whether you have cancer or not, or whether you have cancer type 1, 2, 3, 4, or 5. It doesn't have to be just 2 classes. All right, about out of time. Any questions? Lots of info coming your way. If you're itching to get started, go to course content, notes, topic 1. I'll lecture from topic 1 on Friday. Monday, by the way, I'll post this on eCampus also, but Monday I have an event I have to attend with our undergraduate majors, or with having to do with our undergraduate majors. So I can't lecture live on Monday, and what I do when I can't lecture live is I post a lecture video from a previous semester. So I'll remind you on eCampus, but Monday there won't be a live lecture. I'll ask you on eCampus to watch a replacement video, and I'll see you Wednesday. All right, thanks.